let me go ahead and get things started for our speaker. Oh, I see actually a request has come in through my email that from Dan Caton that I'll actually just answer. The links that brought you to the live talks will not take you to recordings later, but we are planning on offering the recordings on our website. So if you go back to the same TriStar website that brought you here, probably next week, what we'll do is we'll extract the videos and then we'll relink them to Guilford Tech's YouTube channel so that the talks will be available later, but they won't be available immediately. So check back in about a week. Thanks, Dan, for that question. Okay, so let's get ready for today's talk. Dr. Jessica Noviello, she's a planetary scientist and the Nexus NASA postdoctoral management fellow at NASA Goddard. For her dissertation research, she worked on Europa. Well, not actually on Europa, but studied Europa. And she's very interested in all sorts of objects in the outer solar system and even the inner solar system, being a planetary scientist. She's the science PI of a NASA-funded project to study cryovolcanism on Charon and connect this process to other places in the solar system and even beyond in extrasolar systems. You can find her on Twitter at Jessica Noviello. And as an interesting story as to why she's here, one of my colleagues here at Guilford Tech is a GMU alum, and she said, "Hey, there's a talk that their observatory is providing virtually," and this was about a month or so ago. And I saw it and I thought, "Oh, that sounds cool. I'll watch that." And immediately after we were 10 minutes in, I said, "Wow, this is a great talk. I'm going to ask her right now to be a TriStar speaker." And so I wrote her that night, and she wrote back the next day and said, "Yeah, I'd love to." And so we're really happy that you're doing this kind of public outreach, Jessica, and that you were able to join us today. And I'm sure everybody's in store for a great talk. So let me turn it over to you to tell us about cryovolcanism.
Oh, thank you so much for letting me speak today and for sending me that email. That was a really awesome email to wake up to the next morning, and just fantastic news, and always happy to talk more about cryovolcanism and all of the cool ocean worlds of the solar system. And as we'll talk about later, we'll talk about the ocean worlds beyond the solar system as well. So before I begin, can I just get confirmation that you can see my slides, because I feel like I struggled a bit. Okay, excellent, fantastic. All right, well, welcome everybody. Thank you so much for being here today and for listening to this talk. So without further ado, let's begin. Oh dear, I'm getting the spinny wheel of death from my computer. Hang on. There we are. All right. Hopefully that's the worst of the technical problems today. So just to give you a little bit more explanation on who I am. Yes, I'm the NPMP, the NASA Postdoctoral Management Program Fellow at NASA Goddard. My job is effectively half NASA management work and half scientific research. So I really get to see both sides of how science works, right down from submitting the proposal to actually looking at the proposals from the other side. I got my PhD in 2019 from Arizona State University. I took full advantage of getting outside and trying to see as much as I could so that when I looked at pictures of other planets, I had a physical reference in my head that I knew about because I had been there and I had been able to touch it and in some cases even climb it. So I've kind of worked all over the solar system. I've studied Europa, but I've also done asteroids. I've done Kuiper Belt objects. I even did a little bit of Venus. And in trying to think of how all of those ideas came together, the one connecting thread between all of them was water. All of these places are somehow influenced by or have been, or they're influenced by, and they have also influenced water in the solar system. So in effect, I'm just an expert on water in the solar system and potentially beyond. So with this in mind, let's talk about water and ice volcanism, or cryovolcanism. So cryovolcanism as a whole, the basic definition is it's just the eruption of water, ice, and dissolved volatiles. So volatile is a substance that will turn into a gas at a relatively low temperature. So think of things like nitrogen gas and methane gas and all kinds of, even ammonia too, which is probably very common in different cryomagmas and cryolavas. So in effect, though, cryovolcanism is exactly what you would think of if you heard the words ice volcano. And we don't really have a whole lot of ice volcanoes here on Earth, but they are pretty common, especially as we get further out into the solar system. So I'll take you on a tour of those today. And it turns out that cryovolcanism as a whole might be a very important process in the history of different geologic structures on different planets within the solar system, especially beyond the asteroid belt. But there's a big question mark above cryovolcanism because it's true that we don't actually understand much about the details of how it works, certainly not to the effect that we understand volcanism here on Earth. So just lots of questions about it. How does cryovolcanism work on different planetary bodies? It is seen not so much on Earth, but on places like Titan, Saturn's moon, on places like Charon, which is Pluto's biggest moon. It's all over the place, but why is it different and what kind of processes influence these differences? Thanks to the New Horizons satellite that actually went out past Pluto and it's now trailing itself through the Kuiper Belt, it turns out that all of the data that we received from that mission makes that New Horizons data and the fact that we have it from Pluto and Charon, it makes those places very good test bodies to study cryovolcanism because we have the best imaged resolution of these surfaces because of this mission. So, okay. I feel like I'm getting a little bit ahead of myself here because I've been talking a lot about cryovolcanism and different missions and places, but we don't have a good background on what cryovolcanism even is or why it's so weird. And to fully appreciate how weird it actually is, we need to start by talking about what regular volcanism is, specifically here on Earth. So what is it? Volcanism, at its core, pun intended, volcanism is a planet's way of removing heat from its interior. So most planets, especially planets as big as the Earth, most terrestrial planets anyway, they are constantly producing heat, and that heat needs to go somewhere. And volcanoes are a way of releasing heat, in much in the same way that when you get overheated, you sweat. A planet's sweat is effectively its volcanism. So if it helps to think about it that way, there you go. Volcanoes are a very common presence on many different solar system bodies, not just the Earth. We see them on the Moon, Mars, Venus, Mercury, so the terrestrial planets. We also see them on many moons in the outer solar system, most notably something like Io, which is one of Jupiter's moons and actually the most volcanically active body in the entire solar system. And yeah, they're pretty common on things above a certain size, above about 600 miles in diameter. And that again is a function of the heat that's needed to produce these volcanoes. On Earth, these eruptions are driven mostly by pressure and buoyancy. So buoyancy means that something that is less dense is going to push against a more dense substance and actually rise up through it. In the case of volcanism, liquid rock, which is magma, is less dense than the surrounding rock, so it easily works to lift itself up. So it actually can counteract gravity, that buoyancy force, and it pushes it up through Earth's crust, eventually reaching the surface and oozing out or even exploding out as lava or ash or any other kind of volcanic fragment. So that's a really important point that I want you to keep in mind, is that solid rock is more dense than the liquid rock, because we're going to come back to that when we talk about cryovolcanism. So volcanoes on Earth are most commonly found among plate tectonic boundaries. These are the tectonic plates themselves are pieces of Earth's crust that move around, and some are moving apart from each other, some are moving together, and some are just kind of sliding along. All of this heat and all of this friction is being, again, released as volcanoes. So there's the famous Ring of Fire along Indonesia and Japan, the Aleutian Islands, basically down the entire west coast of the Americas. There's a lot of volcanic activity at these boundaries, but it's not the only place where volcanoes can occur, because there are famous hotspots like Hawaii or even Flagstaff, Arizona, that are considered hotspot volcanism. So there are these intraplate volcanic hotspots, and we're still trying to figure out exactly what makes a hotspot happen where it does. This is a really exciting new stage of research that volcanologists are going into right now. And humans have lived around these volcanoes for millennia, despite their danger, because they do replenish a lot of the nutrients that we need to grow things like crops. Volcanic soil is actually very rich in these nutrients that plants need. So there's a hint there of like, oh, maybe we need volcanism to refresh some of the nutrients that life might need on other planets. So there's clearly a lot going on between the interplay of a planet's interior, its volcanoes, and maybe even the life that is living or potentially living on a planet's surface. So here are some examples of what volcanoes on other planets can look like. We've seen some examples of Earth volcanoes on the previous slides. What I have here on this slide is, well, first the leftmost one, the Viking 1 composite. This is Olympus Mons. It's the largest volcano, it's the largest mountain anywhere in the solar system, and it's on Mars. It's 13.5 miles tall, 370 miles wide. So to give you a sense of scale, it's about 2.5 times as tall as Mount Everest. It's massive and enormous, and a volcano. On the other hand, the more orangey picture that's in the middle, those are volcanoes on Venus, and they actually look a lot flatter. They are a lot flatter because of Venus's atmosphere is just so thick. The volcanoes themselves don't actually have the strength to build themselves up to be very tall. So these end up being very wide and very flat. And they actually have the nickname called pancake domes because of this wide and flat appearance. We'd like to know a lot more about Venus and its volcanism, and basically just a lot more about Venus in general. So thankfully there will be 2 new NASA missions to Venus in the next decade. We're very excited about that. And then for one example of a volcano that's not on a planet, it's actually on a moon. The smallest image on this slide in the bottom right corner is Jupiter's moon Io, which I mentioned before is the most volcanically active body in the solar system, and its volcano Tvashtar. So the plume that you see is 200 miles tall, just to give you a sense relative to the size of that eruption to the size of the moon itself. It's just absolutely enormous. And one of the most important reasons that we see a plume like that is because Io doesn't have an atmosphere. So there's nothing stopping the material from escaping into space and creating a plume as tall as it is. So there's clearly a lot of diversity in different volcanoes across the solar system, and it's fascinating to think about how volcanism as a process is influenced by each one of these, by its environment on these planets. Which kind of begs the question of what controls volcanism itself. There are a couple of different categories of contributors for what controls volcanism. One is the magma itself. So what is the temperature of the magma? What's the density of it? What's the viscosity? So the viscosity is like how sticky something is. Something with low viscosity is like water, it flows very easily, but something with high viscosity is like honey. It's kind of sticky. And different properties like that influence how much of how thick different deposits of lava can be. So you can see something oozing like the A'a flows in Hawaii, and that might have a higher viscosity than something that's much more runny, like the Hawaiian pahoehoe. I swear I'm not making these names up. These are the actual geologic terms for this flow. So it's fascinating, again, just how much like the stickiness of lava. Not that I recommend actually touching lava. It's probably a really bad idea. So also details like dissolved gases. So what is it actually made of besides molten rock? The water content ends up being really important too. The crystal content, which is a function of temperature, how many bubbles are in it. It's really complicated, all of the different factors that go into just figuring out what magma is made of. But then there's the eruption itself, which is more of a function of the shape of the volcano. So that's how quickly the eruption is happening, how long it lasts, how much of it exists, the number of different eruptions that can happen over time. There are some volcanoes that erupt once and that's it. They are dormant forever. And then there are others that are more constant, something like Kilauea up until it stopped fairly recently, actually. And then, of course, the number and size of different vent openings. So like how many places is magma and lava oozing out. But then if we go even bigger than the volcano itself, we start talking about the planet. So what is the gravity of the planet? How does that influence how much stuff can flow out and flow up, especially in something like Io's case? The atmospheric presence and its pressure. So do ash particles escape into space directly, or are they kind of flattened down like a pancake dome on Venus? What is the bulk composition of the planet itself, which is where the magma would get all of its magma composition from? And then the heat budget. So when I say heat budget, it's very important. So I'm going to emphasize that it is a very important point. And when I say heat budget, I mean how much heat is the planet producing versus how much is it getting rid of and how much is it actually keeping inside either its shell or in its atmosphere. So this ends up being a really important parameter if we want to understand volcanism on other planets. So here are some heat sources for planetary bodies. We have first is accretion. So that is something like in the beginning of the solar system when we had nothing but this cloud of gas and dust around a protostar. And the gas and the dust started to stick together, very, very tiny, and eventually grew to become a planet. That is the process of accretion. And it's one of the first sources of heat for a planet. And it's a relatively short-lived one because it only happens when a planet is actually forming from this dust and gas cloud. So right now we don't have that happening here on Earth. The Earth has already formed. The Earth has also already differentiated. So differentiation is the process of forming layers and moving that mass around within a planet. And this is a really good little illustration of that happening. So it's as the different layers of a planet are forming, because the mass is shifting around, that actually creates a lot of heat just from friction, but also the release of things like potential energy. So this is another early source of heat in the solar system. And again, Earth doesn't really have that right now, but this was a potentially very important early source of heat for not just Earth, but for many other planets themselves. What we have here, or one of the main sources of heat that we have now on Earth anyway, is radioactive decay, which is when unstable elements in a planet's interior begin to decay and they release heat as a result. So that's a big source of heat for a planet now. Many planets just didn't have a lot of this radioactive material, and that's why they are now, or part of why they are now geologically dead. So this could explain something like Mars, or especially the Moon, which is just much, much smaller. They just didn't have enough stuff to keep themselves warm, and so these planets and moons are now geologically dead. No less interesting, but just not as dynamic as something like the Earth. And then the final source of heat, which is another one of these long-term sources that ends up being really important, especially in the outer solar system, is something called tidal flexing. And I have a whole different slide on that because it's so important. It is actually the most important heat source in the outer solar system. And it just means that when a planet is going, or a moon is going around a different planet or even a star, depending on the shape of its orbit, it can actually change the shape of the planet or moon itself. And this is something that happens in the Galilean satellites that orbit Jupiter, um, especially with something like Europa. So Europa has a 3.5-day orbit around Jupiter, which is the most massive planet in the solar system. And its orbit is mostly circular. It's slightly elliptical. So it's very slight, but it turns out that slight change makes a huge difference. Because every time Europa goes around Jupiter, every 3.5 days, its shell is actually warped by the slight differences in position or distance away from Jupiter. And because of that, Europa's shell actually will flex. And that is tidal flexing. So that amount of movement of its ice shell, which is plus or minus about 30 meters, so it's getting bigger, or it's warping itself by 30 meters every 3.5 days, and that creates a lot of friction, which leads to a lot of heat, which is one of the reasons why we think that Europa is able to sustain that famous liquid water ocean underneath its ice shell. So this is not just something that happens on Europa, though. It happens on almost all of the moons in the outer solar system, but as a function of distance away from their star or their host planet. But then we have some oddballs like Ceres, which doesn't orbit any planet. It does orbit the sun. It's out in the asteroid belt, though. Ceres is a dwarf planet, so it's in the same category now as Pluto. And it was visited by the Dawn mission, and Dawn actually orbited between 2015 and 2018. So it got a lot of really awesome pictures and spectral data of what Ceres' surface looked like. One of the most prominent features on Ceres is this mountain called Ahuna Mons. It's a relatively young geologic feature, only about 250 million years old. So think about like the age of the oldest dinosaur fossils. That's about how old Ahuna Mons is. And we think that there's a lot of evidence that it could be a cryovolcano. And if it is a cryovolcano, one of these ice volcanoes, then it's the closest one to the sun in the solar system. So that's a really exciting detail, and that it might be this close to us. I mean, the asteroid belt is far away, yes, but it's not as far away as Europa, so it's really exciting. But one of the details is that cryovolcanism here might only be possible if there is a high amount of ammonia present. So ammonia is one of those volatiles that you might recognize, because if you ever have to put antifreeze in your car, you want to make sure that there is enough of non-water substances that it will keep the different pipes and functions in your car. It just stops things from freezing. I am really showing how little I know about cars right now, so I'm sorry about that. But the point is, something like antifreeze in your car could help drive cryovolcanism on a place like Ceres, because the less having things like ammonia in the cryomagma will help it flow better, because it won't be as easy to freeze. So here we go with another example of cryovolcanism. I've already talked about Europa a bit, but it's a perfect example of another feature called an ocean world. To give you a sense of scale, Europa again goes around Jupiter, much bigger planet, but it's actually about the same size as our own moon. So imagine our moon, but around Jupiter, and how much different it might look if it was going around a much larger planet than something like Earth. There's an ice shell over a thin global ocean. It's mostly salt water, and the way that we know that it's salt is because all of this red stuff that you see in this picture, that is salt. It has somehow made it from the interior to the exterior. Wow, that sounds a lot like cryovolcanism, stuff on the inside coming to the outside. I wonder what that could be. So that's a big hint that there's some kind of cryovolcanic process. There's definitely something going on. Maybe it's cryovolcanism. I mean, I actually kind of favor that hypothesis, but as an idea, there's definitely some kind of communication between the outside and the inside on Europa. So here are what some of its geologic features look like on its surface. We don't fully understand how these features formed. This was the entire point of my dissertation work, is trying to answer that question a bit more specifically. It turns out that all of these features, they could be related to each other. So imagine something like a dome could turn into a hybrid feature, and then maybe it turns into a chaos feature, which is the one in the middle. So it goes from dome, hybrid, chaos. And that's just one idea, that maybe these are all just different stages along a continuum. But I want to call your attention to this hybrid feature here, because this one feature, it kind of looks like it's a little mountain surrounded by a moat. And it's it's a possibility that this moat kind of feature is actually evidence of a cryovolcano that has effused or oozed out a lot of cryolava, and it has collected in a basin around that cryovolcano. So that could be what we're looking at here with these hybrid features. Now, thankfully, there is another mission going to Europa. It's set to launch in 2024, and that is the Europa Clipper mission. So hopefully when that gets to Europa in 2030, then we will have a lot more information about what these features look like up close, and maybe we'll find more of them that will help us figure out exactly how they form. And if any of them, especially the hybrid features, could be a product of cryovolcanism. But Europa and Ceres are not the only places where where cryovolcanism happens. There's a lot going on around Saturn too. Saturn's one of its most famous moons is Enceladus, which has the famous tiger stripes on the bottom that constantly shoot out geysers worth of water and different chemicals, actually. And we know this because the Cassini mission actually went through one of these plumes and actually got to measure exactly what was coming out of Enceladus's south pole. So it's kind of like Europa in that it has an ocean. We're not sure it's a global ocean, but there's definitely something going on there. So again, we have this like explosive kind of volcanism process happening on Enceladus. It just looks a little bit different from how it might appear on Ceres or Europa. We also have at least one cryovolcano on Titan, which is Saturn's largest moon. And Titan is another interesting feature because it, like Venus, has a very thick atmosphere. So how does that influence what a cryovolcano looks like over something like Europa, which actually doesn't have an atmosphere? I think Titan does have the coolest name for cryovolcano in the entire solar system, and that is Doom Mons. And I only found out recently that that was a name that was actually suggested by Tolkien, or it's a Tolkien-inspired name from Lord of the Rings. So I have to say I love it even more now. If there is anybody looking to write a science fiction novel or a play or something, please set it on Doom Mons on Titan. I just think that would be really cool. But there are other places even beyond Saturn, and this is where our data start to get a little more fuzzy, only because we've only sent one mission to these moons, and it's a little bit sad actually, because they were so cool, and we just haven't been able to get back out there. So the Uranian moons that I have up there, the moons that orbit Uranus, Titania, Ariel, and Miranda, they were imaged by Voyager 2 in 1986. And you can imagine that pictures from 1986 satellites versus pictures from like 2015 New Horizons satellites, you're gonna get a lot better picture from the 2015 one. So what we're looking at here is as good as we have, but we know we can do better. And if we can do better, we're going to see a lot more. And if we can see a lot more, we're going to know a lot more about how these moons work. But even with the little bit that we have been able to see, we know that these places also show evidence of some kind of cryovolcanic eruption. They have what look like could be cryovolcanic features, especially on something like Triton, which is actually Neptune's largest moon. And that was imaged in 1989 by the same Voyager 2 spacecraft that 3 years earlier had visited Uranus. But Triton especially is one of the best examples of cryovolcanism in the outer solar system, especially because of these big, large plains that appear as if they were just completely covered with a smooth kind of material, something like what you might see if there was a new part of Hawaii being created by a volcano. And so as we go further and further into the outer solar system, we have more and more examples of cryovolcanism. It is clearly a very pervasive and important process, especially on these ocean and icy worlds, but there's some big questions about cryovolcanism. The biggest one is, how does it even work? Remember when we talked about buoyancy when we were discussing volcanism? Well, unfortunately, that doesn't work with water so well. Solid ice or solid water, which is ice, is actually less dense than liquid water. So that ease that, or the relative ease with which the liquid rock can rise through the solid rock doesn't work so well for cryovolcanism. So okay, well, if buoyancy doesn't do it, then what about pressure? So that is probably what's driving cryovolcanism on all of these different worlds, is that there has to be some kind of internal pressure actually pushing material out. And that's probably what's going on. But then it's like, well, what kind of pressure could that be? And it just spirals from there. But we also don't know what the typical cryomagma composition would be. So what is it made out of? How sticky is it? How many volatiles does it have? What's its gas content? How much cryolava could be released on a typical eruption? How often does cryovolcanism happen on a planet? All of these questions, they're really good and fundamental questions that we just right now don't have answers to. And partially it's because, actually mostly, it's because we don't have a lot of data, especially for some of these more distant worlds where cryovolcanism might have been even more common. But we're working on that. So to emphasize, cryovolcanism is a fundamental process that we still do not fully understand. And yet it is present in so many places in our solar system. So there's a big question here about how does it work? And it's a big area of active planetary science research right now to try and figure this out. So here's our idea for figuring it out, and it actually centers a lot on what the New Horizons spacecraft sent back from Pluto. So what we have here is, well, I write the Pluto system, but it's really just Pluto in these pictures. The New Horizons spacecraft is on the left, Pluto itself is on the right, or in the middle, sorry, and then on the right is Pluto, but with seen in different spectral bands with which illuminate where different types of ices are. So unlike on Earth, which really only has things like water ice, the H2O shown in blue, unless we were to make something in a lab like dry ice is actually carbon dioxide solidified. That's a really cool substance. I do hope I get to like play with it at some point in the future for lab work. But the point is that different ices will condense at different temperatures. And out in the very far reaches of the outer solar system, 40 times as far away from the sun as Earth is, we can naturally find things like methane ice, nitrogen ice, and carbon monoxide ice. And that's actually what Pluto has in abundance. So clearly, there's a lot of ice and there are a lot of volatiles because maybe with a little bit of heat, things like methane, nitrogen, and then carbon monoxide might have actually been gas at one point. But I specifically want to talk about Pluto's largest moon, Charon. So Charon is about 750 miles in diameter. It co-orbits Pluto. They kind of do this binary dance together where they're both co-orbiting a central point that isn't within either body. That's very unusual for a planet and its moon. It's actually the only observed system where that happens in the solar system. Charon's overall density suggests that its interior is a mix of ice and rock, and it's likely differentiated. So already we're starting to think, okay, if it's differentiated, then it might have had a lot of heat at some point, since differentiation can generate lots of heat. We can also see from the data that we received from New Horizons that Charon's surface is dominated by the water ice that we saw, and it's about 10% ammonia-bearing ices. So ammonia, now we're thinking like that antifreeze that came out. Okay, we're starting to put together a story here. So again, ammonia lowers that freezing point of water, which would have assisted with cryovolcanism happening on Charon. And there's more than that, though. There's more than just the compositional evidence. We also see a lot of the geophysical evidence, too. Let me flip back one page. If you look at this picture of Charon, you'll notice that there's a big ridge going diagonally up. Actually, from your perspective, it would go like this. That ends up, from what we can see, which is only about 40% of the moon. But from what we can see, it does seem to divide Charon into a northern half and a southern half. And the northern half is called Ozterra. It's rugged, it's fractured, lots of blocks. But then the Vulcan Planitia side, which is to the south, it appears to be a lot smoother. And we already are thinking, okay, if it's smoother and we know that there could have been heat and ammonia, maybe there's something like cryovolcanism could have happened. This could be just a cryovolcanic plain that we're looking at here. And we also see in Clark-Montes and Kubrick-Montes, which are those two sections that are outlined in blue, those kind of look like those hybrid features that we saw back on Europa. It looks like a mountain in a moat. So maybe this is yet another example of cryovolcanism. It's yet more evidence for it. I actually have a more blown up picture just in case it was a bit too small to see on the other slide. But again, we're seeing the mountains and the moat kind of idea that we already saw on Europa. And then on the left or on the right, what I am showing you is some pitted terrain. So that we don't 100% know what it is, but it could be that as the cryo lava was flowing out, there were some gases that were being released from the cryo lava itself. And that gas, once it released, it actually, the cryo lava itself kind of froze around where those bubbles used to be. And maybe that's what we're seeing here in this pitted terrain. So if that were true, could it be evidence of gas escaping from the cryolava? And then we asked the question of how much gas could have escaped and what kind of gas escaped. And the problems escalate and escalate, but in a very exciting way. So here are some fundamental questions we have for Charon. One, that Vulcan Planitia, which is that southern area, it was covered with relatively smooth material made of ice and ammonia. So that has been interpreted as a massive cryovolcanic flow. But we also know that Charon might have been able to sustain an ocean. And when that ocean froze, because ice expands when it freezes, that might have exerted all of that pressure that we need for cryovolcanism to happen. So that strain of 1 to 2% actually pushed outwards on Charon's crust. And whatever parts of the ocean hadn't frozen yet needed to go somewhere. And again, it's just going to kind of ooze out because it has to leave the planet. There's no room for it anymore, so it's just oozing out. So maybe cryovolcanism wasn't driven so much by buoyancy, but by the pressure caused by that freezing ocean on Charon. Unfortunately, there are a couple of issues with these ideas, and mostly it comes down to the timelines don't line up. From crater age estimates, which are made by counting the different craters and the different sizes of these craters and extrapolating based on some laws of physics and impact cratering, trying to figure out how old these surfaces are. And even with the billion-year error bars of it's about 4 billion years old, and it could be as young as 3 billion. So again, plus or minus a billion years, it's a very, very wide age. But then different modeling, geochemical and geophysical modeling of Charon to try and figure out when that ocean would have frozen to create that cryovolcanic eruption. Those eruptions wouldn't have been able to happen until at the earliest 2.5 billion years ago. So again, there's 500 million years at least of time between when the age of the surface as counted by craters and when models say the ocean would have frozen. So that's a really big deal. And it turns out that that is what we call a knowledge gap. And the proposal that we put in to study that knowledge gap and to figure out why it exists, that's why we put in the proposal at all, is because we wanted to figure that one out. So here's what we propose to do. First, we're going to look at the craters themselves, and we're going to ask the question, are these regions lower density in craters just by chance, or could they have been overprinted by cryovolcanism? And the second thing we're going to do is we're going to look closer at those geophysical and geochemical models. And we're going to track how Charon's interior has evolved over time using a code called icy dwarf. And then the final thing we're going to do is we're going to look back at all of these other places in the solar system where cryovolcanism could exist or probably did happen. And we're going to try and figure out why Charon looks different from something like Ariel, or looks different from Triton, or looks different from Europa. So there's three different topics being tackled in this proposal. I have not, unfortunately, started this work yet. It comes down to a lot of like technical issues and switching jobs. But hopefully, if you have me back in the future, I'll be able to tell you all about whatever I discovered with whatever we discovered. So the team is just a really fantastic team. I'm going to pause for a minute just to highlight how amazing they are. Steve Dash, Kelsey Singer, Mark Navu, and Lene Quick. They are all experts in cryovolcanism and different kinds of modeling and craters. Best team ever. So just really excited to see what we do, and I hope you follow along to find out with us. All right, so we've talked a lot about ocean worlds in the solar system, and I've kind of thrown that word around without fully explaining what it is. But by definition, an ocean world is a terrestrial planetary body that contains a substantial amount of water, either in an ocean, like something like on Earth, or in a subsurface ocean, like something like Europa or Titan. And because of all of the water that is necessary for a process like cryovolcanism, the connection between these ocean worlds and these cryovolcanically active worlds must be very, very strong. And a lot of that link comes down to just the heat budget of the planet, how much activity the planet is doing in terms of heat. We don't actually have a whole lot of data to study this. We do have a lot of ocean worlds in the solar system. We have a lot of places where cryovolcanism could have happened, but we can do better by studying other worlds. And this is where we start talking about exoplanets. The huge and vast amount of data that they can bring us about cryovolcanism and about just astrobiology in general is so compelling. And it's like when we have so many good examples in our solar system, but then when you expand out and you see what the diversity of some of these places could look like, it's just mind-blowing to me. And we're up to almost 5,000 confirmed exoplanets. We might even be at 5,000 now. I haven't, the numbers haven't been updated since late February, but we'll see. So when we talk about exoplanet and ocean worlds, though, we don't actually have a great analog for what these giant worlds would look like. We know what ocean worlds look like when they are the size of our moon, so something like Europa. We know what they look like kind of when they are a Charon-sized object or something like a Triton-sized object. But what about an ocean world that is the size of a Neptune? What does that look like, and how much heat does that produce, and how does it work? What does cryovolcanism, is cryovolcanism even active on a world like that, and how much activity is happening there? We don't have a great analog for it in our solar system, and the only way to get there is to study worlds like, I mean, we have to base it on something. So we can study ocean worlds in our solar system and try to use it to explore what other ocean worlds might be like, even if they're going to be fundamentally different from what it is that we see in our solar system. And I throw up Earth at this point to just show you how difficult it is to image some planets that are around Earth size. And part of that is just like an imaging bias that we see, where it's easier to find big planets that are closer to the host star. However, with the launch of new missions like James Webb and in the future the Nancy Grace Roman Space Telescope, we're going to learn a lot more about exoplanets that up until now have been very difficult to image. So we also should briefly talk about what it means to be a habitable planet, because it is such a hot topic in planetary science and exoplanet science today. So the habitable zone is defined as the range of distances from a star on which liquid water could be or should be stable on a planet that is Earth size. So like Earth, if you had an Earth-sized planet, water would be stable on its surface if it was in the habitable zone. That does not mean that a planet is inhabited. It just means that liquid water is stable. And for different stars at different temperatures, that habitable zone is going to change. But of course, different stars aren't always the exact same temperature for all of their lives, especially when they're young stars. They're much more energetic, which means they're going to be a little bit hotter too. So the habitable zone changes throughout a star's lifetime, not to mention the fact that planets themselves can also move around. So a planet could go into and out of the habitable zone, which does make it an interesting problem of, like, could a planet be inhabited? And it might even be a function of time as much as position and composition. So what does this mean for something like cryovolcanism, though? It could potentially mean that a planet would become more or less cryovolcanically active depending on its distance from the sun or from its sun. So these are just, I'm putting this out there to give you an idea of how complicated things, questions like, is this planet habitable, really can be. But some of the best examples of potentially habitable planets are found in the TRAPPIST-1 system, specifically planets E, F, and G. Now, this is a very unusual system, at least compared to our solar system. Our solar system ends up being quite weird. There's nothing that we have discovered that is quite like it. And the entire TRAPPIST-1 solar system can fit very snugly within the orbit of Mercury in our solar system, just to give you a sense of scale of how close these planets really are to their star. And keep this in mind for this one last point about how many exoplanets could be ocean worlds, how many of these places could be volcanically or cryovolcanically active. And that's a question that Lene Quick et al. In 2020 looked at 53 of these terrestrial planets, up to about 8 Earth masses and twice Earth size in terms of radius, considered all kinds of tidal and radiogenic heat, so all of these different heat sources, and found that all 53 of these places should be cryovolcanic or just active somehow, whether it's volcanically or cryovolcanically active. And more than that, about a quarter of these places could be ocean worlds. So not only are they geologically active, but some of them could sustain these large liquid water oceans. And that is a really exciting statistic, because if we look at exoplanets, if as many as 26% of them could be ocean worlds, and then the potential for life, for finding life one day, exponentially increases, where our odds are starting to look they're still pretty bad, but they're not so dire as they used to be. It's a very big world out there, or universe even. So then why does this work matter? I've kind of touched on it in a few ways. We need to keep studying volcanism because volcanoes bring up material from Earth's interior that otherwise we'd have no way to sample. The volcanoes and cryovolcanoes put gas into atmospheres that might be visible with future telescopes, so especially something like James Webb. All of that dust and gas that could erupt from a volcano, maybe we can image that and we can learn a lot more about what's going on a planet's interior just based on what it's kind of spewing out into its atmosphere. Volcanoes, along with plate tectonics, they're responsible for cycling nutrients that may be necessary for the generation of life. That the ocean world's link to cryovolcanism is very strong. You can't have cryovolcanism without water, so not too much water anyway. So I hope I have argued then that studying cryovolcanism is an important aid in the search for life. And I will just leave my last slide up, and I think I will stop there and take questions.
Thanks, Jessica. That was great. So we have a number of questions in the chat, so I can sort of work through some of those. And let me encourage anyone who has questions, go ahead and type those in. First, I want to ask about these modes. So the profile of these is they go down and then up?
So on Europa, we don't actually have topography data. And actually, I don't think we have it on Charon either. we don't have something in the way of something like LIDAR, which are like radio pulses that go down and directly measure the height of different objects. The way that we have estimated the height of things like Kubrick and Clark-Montes is from something called photogrammetry. So we take two images that are slightly offset and we actually can make them 3D and estimate the sizes from there. And that does suggest that the moat is depressed, or sorry, I'm specifically talking about the moats of Clark-Montes and Kubrick-Montes on Charon, that yes, it does look like the mountain itself is at least 2 kilometers above the rest of the relatively flat surrounding terrain, and that there is a dip along the moat. So I don't think it's quite as severe as 2 kilometers. It's probably like half a kilometer or something, but it does look like a lowland. And if it is a moat, then if it's 500 meters shallow,
Right.
then it would have been filled up a little bit. So potentially it could have been even more shallow.
So has something subsided there? Did something flow in there and then sublimate away? What?
We're gonna have to figure that out. Maybe it could be that the Clark and Kubrick Montes are the cryovolcanoes themselves, and they just kind of, as they were forming, they actually bent the lithosphere of Charon
Oh,
down,
wow. Okay.
and then created it themselves through multiple cryovolcanic eruptions, or maybe they were just really big features, and then a cryovolcano from nearby oozed out and filled in everything except what we see today. We are going to have to figure that out.
Wow. So here are, let's go through some of the others. How tall are the large volcanoes on Io?
Oh, how tall are they? Uh, I am so sorry. I don't have a good answer for you here because I don't know. I am okay. Well, I feel
Would
like I have egg on my face right now, but I would guess about a few kilometers.
would
They have.
they, there's lower gravity there,
Mhm.
but there's a lot of flexing, I guess. So would they sink back into the
Ooh, this is such a good question. Okay, I'm going to answer it as best I can. I do know that there's a lot of evidence that suggests Io, instead of having a liquid water ocean under its crust, it actually has a magma ocean under its crust. So it is almost certainly being influenced by the weight of the volcanoes that are on it and constantly pushing down on a relatively squishy kind of magma ocean. I don't know exactly what that kind of deflection looks like. That sounds like a geodynamics question, and I admit that's not my strong point.
Okay.
So I would say though that it's a safe guess that the volcanoes are probably a few kilometers tall, and they're very very active, and there are probably a whole lot of new volcanoes that we haven't yet seen because we haven't been looking for them, and Io is a very cool place to study.
So we have another that asks, are there any volcanoes on Mercury?
Yes, there are. They are also not active anymore, and I'm so sorry, I'm not an expert on Mercury's geology, but I do know that there are volcanoes on Mercury. I probably just couldn't find a good picture, or else I would have had that. Yeah,
Um,
Mercury is just a really weird place to study anyway.
mhm. The so we have a question about the Steve Dash that and was asking, is that Steve Dash from Guilford Tech or Steve Dash from Arizona State? That's sort of an inside joke here, and you know a little bit about that, right?
Mhm. Yeah, so I mentioned that Steve Desch was, he is actually the PI of this Charon cryovolcanism grant. So it's funny. I do mean the ASU PI, or the ASU Steve Desch.
So many of you who are regular TriStar attendees know that Steve Dash also works here, or another Steve Dash works here, and not the Steve Dash at Arizona State, who our speaker has worked with. And so we were fortunate enough to have that Steve Dash join us last November for a talk on Oumuamua, And that talk, if you missed it, is on Guilford Tech's YouTube channel. So if you want to go back and take a look at that and see two Steve Dashes on screen at the same time. The photo of Pluto shows different areas for CH4CO and H2O ice. Are these ices immiscible?
Ooh. That is a really good question. So immiscible as in unmixable, they don't like
Right.
mix together. Okay, just making sure. I do know that what we were looking at were a lot of like the surface ices. I don't think they, okay, I don't actually have an answer here. This is a chemistry question. I don't have a good reason why they wouldn't be mixable or why they shouldn't just mix together. I would expect the temperatures of like their freezing temperatures to change. I do know that lots of places on Pluto are covered with glaciers worth of ice. So it might just be that different parts of the glaciers have different compositions of ice on their surface. Wow, I love getting questions because it exposes all that I don't know. So I'm wondering now then what that does mean. I don't think they're immiscible. I don't, and I do know that that Pluto is covered in glaciers, and I'm not sure I can say more than that. I just don't want to give a wrong answer either here.
Are they overlays of different detections?
They would be different different wavelengths and different. So the data that comes back from the spectrometer would have different band depths that correspond to different kinds of that corresponded to the different kinds of material that it was looking at. However, um, I don't know what the error bars on that could be, and I mean they were all. It was just a flyby mission, so it got like one pass at everything, and whatever it saw, it saw. So it wasn't taken with different instruments though, so it was all kind of taken at the same time with
Okay.
at different wavelengths, and they might just be extrapolating from there. I also don't even know what the spectral resolution is of these spectrometers. Okay, again, thank you so much for these questions. I feel like I'm not answering them very well at all, but I really appreciate how engaged everybody was with the talk to be asking these questions. So thank you.
So here's another one. Having a mission to the Uranian system will really help your research, it seems. What are the prospects or timelines for such a mission?
Oh, I'm so sad. Okay. This is fantastic. On the last Discovery round of missions, there was a mission proposed not to the Uranian satellites, but to Triton, and it was called Trident. So it was one of four that could have been selected, and NASA chose to go with Veritas and Da Vinci, which are both going to Venus. I definitely didn't expect two Venus missions. I can't say I'm unhappy about that, but I am sad that the Trident mission did not get selected because it has just been so long since we went to the outer solar system. And the biggest problem with missions to the outer solar system is how long missions would take to get out there. So it's very possible that somebody who proposes a mission, let's say next year, maybe it takes 15 years for the mission to actually reach its destination. And it's very possible that the person who proposed the mission isn't even working in the field anymore. You know, they've probably retired by then just because it takes so long to get out there. So there is a very strong push in the ocean worlds and outer planets community within planetary science to get one of these missions to go out to Uranus or Neptune. Um, Ideally both, if that was possible, that would be fantastic. So, like, yes, it's something that we would really, really, really love to have, and we keep trying. It's just been very difficult so far. I have hope, though, that, you know, in the next decade we might start to build a mission there, but it might not be until something like the 2040s that we even get the data back from it.
And that has such an impact on what you're proposing to study because, I mean, you have the Pluto flyby images that you're just going to keep looking at, and you have I mean, there is going to be the Europa Clipper mission, which somebody's asked about actually to describe what it's going to involve. But you won't have any new data coming in from any of these worlds in the outer solar system to really inform what you're doing. So it's got to make it hard.
Yeah, it's definitely frustrating. So it's why I think the question of cryovolcanism hasn't been answered yet, is because up until we got the data back from New Horizons, we didn't have the right capability. We didn't have anything really. We just had some pictures, which isn't always enough. But finally getting some data back from the New Horizons mission in 2015 of Pluto and of Charon, that finally gave us the ability to ask these questions a bit more formally. And I mean, it's still not perfect, but it's a lot better than we used to have. And clearly there's a lot more that we still need to know.
Um, Cryovolcanoes on Earth, or could there
No.
be if a
No, the Earth is actually a little too warm for ice volcanoes. We do have a lot of glacial volcanoes in places, especially like Iceland. And I know that Brittany Schmidt at Georgia Tech actually does field work to Iceland to study this, but that might be as close as we can get. But even then, it's a volcano. It's an actual rock volcano underneath a glacier. So these are special kinds of features called yokolops. Um, I probably did not pronounce that right. It's an Icelandic word, but the idea is that the heat from the volcano is constantly melting the glaciers on top of it, and it's an interesting dynamic between ice and fire. Um, but no true cryovolcanism on the Earth, sadly.
what would you like to see studied in an outer solar system if you were to propose your own?
Ooh, I love these questions. Okay, the first thing that any planetary mission should have is a camera. Um, and I would fight for a couple of cameras, actually. I would want one to get a couple of cameras that do different things. I want one camera that does more wide angle imaging, which is pretty standard, and one that does more narrow angle imaging to get like higher resolution, but of fewer places. And then the wide angle camera can get a bit less good resolution, so a bit coarser, but it gets more places. And honestly, we know so little about the outer solar system that even getting pictures back would be super helpful. But we should also have things like a spectrometer to tell us what the surface is made of. I personally would love something like a ground penetrating radar to tell us how thick the crust is, or if we're looking at an ice world, how thick that ice shell is. The glaciers on Pluto, how deep do they go? And we could learn that from things like ground penetrating radar. Again, the tricky part about the outer solar system missions is because they take so much fuel to get out there, there's not a lot of mass in the budget for things like science instruments.
Hmm.
So, I mean, if I could only have three, I would have an imager, a spectrometer, and a ground penetrating radar. And I feel like anything on top of that, like maybe a magnetometer to study remnant or even active, probably not active, but maybe there was a past magnetic field that we could still detect in the different rocks on the surface, and that would be really cool. Especially for something like Enceladus that has plume activity, and even Europa, which probably also has plume activity. So something like a dust analyzer, or something that can ingest some of that material and actually analyze it, like what Cassini did with Enceladus's plumes. Although I should say that Cassini wasn't designed to do that. They just figured, we're already here, why not try? And to have a mission that is designed to do that would be really, really cool. So that's my answer, is like anything that you can find, but mostly a camera.
So where would you go if you had to pick a place,
I have to pick one place. Oh,
or one system?
one system. I think I would go to Triton. Honestly, there is a lot of weird things about Triton, not just its cryovolcanism, but the fact that we are pretty sure it is a captured Kuiper belt object. One of the biggest pieces of evidence for that is the fact that Triton actually rotates in the opposite direction around Neptune as every other moon in the solar system. So it's already kind of weird. So if we go to Triton and we find not only evidence of cryovolcanism, but but maybe some interesting things about its dynamical history. And we can also potentially learn about a Kuiper Belt object. So it's kind of like 2 missions for the price of 1. We're getting a moon and a Kuiper Belt and cryovolcanism, which ends up just being the icing on the cake.
There's a lot of tectonic rifts on these worlds. Would these usually be associated with cryovolcanism as the plate tectonic boundaries are on Earth?
Most of these places, they do have tectonic features, but they're not necessarily tectonic plates. Europa especially has evidence that its surface is being recycled somehow, and that's a special process called subsumption. So not subduction, but subsumption. And this is one of those areas of active research where it's like we think it's happening, but we need to know more about it. On something like Charon, which is what I have on the screen here, all of those little ridges that you see are things called graben, Graben. And we think that those formed when the ocean on Charon froze and the crust actually extended. And when it extended, it actually broke apart. And that break that you see, or those breaks that you see, those are the grabens that you're looking at is caused by those breaks. So again, not necessarily tectonic in origin, but definitely geophysical in origin.
And cryovolcanism on Pluto?
Probably. I haven't looked at Pluto well enough to know for sure, but yeah, probably. Maybe even on the parts of Pluto that we didn't get to see on the flyby.
Okay, so someone has asked, Karen, Sharon, or Sharon?
Oh goodness. I have heard, and I have said, I think even in this presentation, I think I've said all 3. The official story that I have heard, actually I shouldn't say official, the rumored story that I have heard about this is that it's named after somebody's wife, but it's, and I think her name was Charon. So I think this is just I think it's supposed to be Charon, but if you want to do the Greek mythology of Charon, totally fine with me too.
So I know the story. It's Jim Christie who discovered Charon's wife's name was Charlene. He called her Char. And so he named it after his wife. This story actually, Jason Ibarra was our first speaker, and he edits the This Month in Astronomical History series for the AAS. Someone wrote that story up at the This Month in Astronomical History. So if you Google that and find that series of articles, you can see the background on that story.
That is so cool. I honestly thought it was a rumor. It's true. Wow.
So we're a little bit over time. Here's another one. Can Webb answer some of your questions? If so, which ones?
Oh, Webb is going to be amazing for exoplanet science, and I think it's going to be able to tell us a lot about the volcanic activity of other exoplanets. I don't think it's going to be able to tell us more details about cryovolcanism on Charon or Charon, as I should probably start calling it. It's a very powerful telescope, but to look at anything, you need to put in a proposal for James Webb to point to a specific object. And it needs to be a very compelling proposal to do that. And I'm not saying that the science would not be compelling. If it were if I were to say, to ask it to look at Charon, but they would probably turn around and say, you're not going to do better than the New Horizons stuff, and you already have that data, so you're probably not going to get it. And I don't think they would be wrong to say no. I don't think we're going to get better than the pictures that we got from New Horizons. I think where James Webb would be most helpful is in looking for those volcanic and cryovolcanic signatures in exoplanet atmospheres. I think if we see an awful lot of volatiles for things like nitrogen and ammonia and even carbon monoxide or carbon dioxide gas, to have a thick atmosphere at all means that there is an active interior to hold onto the atmosphere via something like a magnetic field or and a high and enough gravity to actually hold onto those gases. And then the fact that like Earth's atmosphere is relatively thin, especially compared to something like Venus's atmosphere. And Venus's atmosphere is so thick because of all of its sulfur-based volcanism that has happened. So if we look at an exoplanet with a thick atmosphere, we're probably looking at exovenuses, and what their the composition of those atmospheres is going to tell us a lot about what kind of volcanism is going on at the surface. Again, if it's more sulfur-based, it might be more like a Venus, but if it's more like nitrogen and methane, we might be looking at something more like Titan, which does have cryovolcanism on it. So so it would answer those questions at a very broad level of what are exoplanets made of.
Okay, I'll do one more. Someone has asked, volcanisms are really sort of a surface process. What can they tell us about the core of a planet?
Ooh. So they mostly tell us about the mantles of planets. We do know that the core is there mostly because of the magnetic field that we see generated on Earth and other planets. But the most of volcanism, actually, the action happens in the mantle. So it tells us about what circulation is going on in the mantle. It also tells us what kinds of minerals are being created in the mantle. A lot of these minerals, something like peridotite, which you might know by its gemstone name peridot, that I think it's the birthstone for October, actually. So it's a mineral that actually formed in the mantle and has been brought up through volcanism to the surface. So we would not have peridot, we would not even know it existed unless we had those volcanic rocks. So a big part of what we learn about the Earth comes from volcanoes and just what they bring up to the surface, and specifically like what is down there that we wouldn't otherwise know about. And then the other thing that really matters for volcanism is just that the mantle itself is always moving around. We think that plate tectonics themselves are driven by mantle convection. So what actually drives plate tectonics is a really big question in earth science, and I am vastly oversimplifying it. But there's definitely some kind of connection between the movement of mass in the mantle and the fact that things are moving at the surface of Earth itself. So we're kind of getting a lot of information just by looking at volcanoes on Earth, it's amazing, and it can be very, very dangerous to study volcanoes, and yet so rewarding because of what you learn. I have a friend, Kara Brugman. She's a scientist at the Carnegie Institute here in Washington, D.C. She actually does laboratory work trying to figure out what magmas look like on exoplanet worlds. The research is really phenomenal. She does a lot of chemistry that I don't understand, but it's just really cool to talk about it. And like, hopefully the two of us can work on an exoplanet project in the future. But I say that to give you an idea of how people are taking knowledge from Earth and applying it to exoplanets. I think you're muted.
Turn myself off. Let's wrap it up there, since people want to get a little bit of lunch before our 1 o'clock talk. Thanks so much. This has been a great presentation, and the Q&A was outstanding as well. So we're really glad you could join us, and are excited about what you're doing, and we wish you great success in your future research. Let me mention, for those of you interested in it, the astro imaging contest is going to open up in about half an hour for voting, and so check the link at the TriStar page, or I put a link in this chat. It's up near the top of the chat, to go over and look at the images and start thinking about which ones you like and cast your vote, and the winners will be announced at the end of our last talk today. The upcoming talks, 1 o'clock, Diana Hannakainen from Sky and Telescope will talk about radio astronomy, and then also we'll talk about Sky and Tell in the Q&A. And then Britt Lundgren will speak at 3 o'clock about galaxy evolution. And so that's the afternoon schedule. So we'll end it here. Thanks again, Jessica. This was great. And we'll see everybody this afternoon.